Welcome everybody. Today we have the pleasure to host Nicolò Lucchesi. Nicolò recently graduated in computer science at University of Pisa, defending his master thesis about Avalanche-RL, extending Avalanche for Continual Reinforcement Learning. So I think this is quite an interesting work, since there are not many libraries around that support this kind of functionalities, so continual learning and reinforcement learning experiments. So I'm quite interested in seeing the results he got from his thesis. So let me thank again Nicolò for being here today, and I will now leave the stage for his presentation. Nicolò, you can start whenever you want.
Okay, thanks Andrea for the introduction. Hope everyone can hear me. And so yeah, I'll be presenting my work on Avalanche, extending Avalanche, so to get to a continual reinforcement learning framework, and also the side effect, let's say, which was Continual Habitat Lab, which is a highly realistic benchmark. So first off, let me introduce myself. So very briefly, this is how I normally look. And graduated last month, so short of a month ago, and thesis regarding AvalancheRL, so the extension of Avalanche to reinforcement learning, and currently working as an AI software engineer. And I've had some very short, let's say, experiences with other meetups as well. So getting right into the, let's say, the focus of this talk. The motivations behind the work are those that in most recent years we've seen a rise in interest in publications regarding continual or lifelong reinforcement learning. And despite that, the scene still lacks a, let's say, central reference in terms of for practitioners and researchers alike. So this is, we decided to focus on tools and benchmarks that would let's say, enable those people working in continual reinforcement learning to just help the growth of the field. And brief outline of this presentation. First off, start with some very short background notes. Probably have to skip even the continual learning part. And then we'll delve right into the details of AvalancheRL and Continual Habitat Lab, and then finally close off with some experiments and thoughts on future work. And so continual learning, as I said, I'm sure everyone's quite aware of what continual learning is here, but still, just for the sake of simplicity, we deal with a continual stream of what we call experiences. So we have a stream of data, and this data is conveniently organized into experiences. These experiences give access to a data set at some point in time, and may have this, let's say, give access to this data for just a short span of time. And continual learning is all about incrementally developing knowledge. And we always deal with what we call non-stationarity assumption, as the underlying data generation process may very well change from experience to experience. Let's say continual learning tackles the challenge which is represented by catastrophic forgetting, so the tendency of artificial neural networks to forget what they've learned before upon arrival of new information. And obviously we have to do that in limited computational memory budget. And reinforcement learning, on the other hand, is a very well-known machine learning paradigm in which it is formulated as an agent interacting in an environment, so taking actions in an environment and receiving from the environment a scalar feedback in the form of a what we call to be the reward, and some observations which represent the observable state of the environment itself. Reinforcement learning is usually used to tackle sequential decision-making problems. So all those problems that require, let's say, to take multiple actions in time, And it does so by maximizing the collected rewards along the way. And reinforcement learning is said to deal with non-stationarity in an inherent way, because the data generation process is directly influenced by the actions that the agent can take in that environment. And reinforcement learning, let's say algorithms are well known to be very high sample inefficient. And continual reinforcement learning, on the other hand, takes a bit the best and the worst of both worlds. So we now have an agent which interacts with an environment, and it has to learn from a sequence of experiences in order to learn potentially unlimited amount of new tasks. And it has to do so without, let's say, forgetting what it has learned before. So tackling the catastrophic forgetting part, let's say, from continual learning, but also doing that in an efficient, way. So we also have the additional high sample inefficiency that comes from reinforcement learning. So this is probably where the difficulty in the field lies, and why it hasn't been explored that much so far. And the object, though, is still the same as the one we have in reinforcement learning. So we're still trying to maximize the collected rewards. And AvalancheRL is born to do exactly that, to help, let's say, designers to practitioners and researchers to design algorithms for continual reinforcement learning. And its structure is the following. So we see in the picture a few of the main features of this, let's say, framework, based obviously off of Avalanche. And what we did is that we had to, let's say, build an abstraction over the task stream. So the agent learns multiple tasks, and we have to somehow give access to the user to this, let's say, task stream exactly. And we did so in the benchmark model. So here, essentially, with the RL scenario part, we give access to an experience stream, and we were able to essentially leverage what the Avalanche module called benchmark already did for the supervised and unsupervised part. But the true difference here is that we're not given access to a data set anymore, but instead we're given access to an environment. So now we have, if you want, a stream of environments, and the agent can interact with this environment and learn off of this interaction. In order to do so, the algorithms which the reinforcement learning algorithms are all, let's say, implemented from scratch in what we call the RL strategy component. Essentially, this, for those familiar with Avalanche structure, this is a, let's say, a subclass of the base strategy in the training module. And what it does essentially implements and abstracts away algorithms and offers, obviously, a huge amount of callbacks, as in Avalanche flavor. We also implemented a way to generate this data in a parallel fashion, and we call that, let's say, component vectorized environment. This is because we essentially, this is a sort of tribute to the inspiration from Stable Baselines Tree, which has something similar, but based on Python multiprocessing, while instead we, as a backend, as a parallel and distributed computing library, we chose Array instead of multiprocessing. And then we also have benchmark generators, which allow you to easily create a benchmark. And focusing instead on this, on the RL-based strategy component, what we had to do here is to give the user a way to abstract any reinforcement learning algorithm. And we did so with a very simple two-stage pipeline. We have a rollout phase and followed by an update step. Now, the rollout stage is where the interaction with the environment happens, and where we generate new observations, new data. of this interaction. And the update step is instead the computation of the loss. Then we optimize during learning. And we can then implement any reinforcement, any model-free reinforcement learning algorithm by subclassing these two steps and implementing any, let's say, variant of that. So the rollout phase is quite static, actually. We can parameterize that well, and we can have the agent interact in parallel with the environment and generate data, while the update step is all about the specifics of the algorithm, since it has to compute a loss. We also gave much thought into data structures for state transition. So many reinforcement learning algorithms, such as DQN, for instance, will have to deal with what is called the replay memory or replay buffer, or anything like that. So we designed from scratch all these components just to make sure that they're efficient and in terms of tensor processing, and that they're let's say and they're processed right when needed. So we essentially wait until the update step to do any let's say reassembling of these tensors and get them into the GPU, while on the rollout phase they're just pushed and let's say stored just to avoid any latency. And this is a bit of a flavor of what AvalancheRL is in practice. If you're familiar with Avalanche, you're probably going to see something very similar here on the code part. Essentially what we do, we can create a model choosing from one of the pre-implemented neural networks. We can then generate a benchmark by using the benchmark generator, which essentially here creates a cadpol environment, which composed of a single experience and one parallel environment. So it's very easy. And the strategy, so we pick an algorithm, and let's say the first implementation of AvalancheRL allows to select among A to C and DQN plus some DQN variants. And then we train with the usual training loop, and essentially we alternate rollout and update steps as we explained before. The second part of the thesis is instead focus on what we call Continual Habitat Lab, which is a highly realistic benchmark, and it's essentially uses Habitat Sim, which is a 3D engine to essentially simulate these 3D indoor scenes, which are usually taken from real world, let's say, places such as this apartment, and they're then re-rendered, and an agent can easily and freely roam around these areas and essentially collect observations. And the key component here is this is very highly realistic environment, and this is sort of a, let's say, a challenge for modern algorithms to learn from this kind of highly, let's say, realistic data. And it was specifically designed for continual reinforcement learning, and this means that we redesigned all, let's say, the concept of task and how to bundle multiple tasks in a task string. And then we also went to, let's say, great length into defining how scenes can change. It's essentially how the environment can change as to learn in a continual way. And it is all very configurable through a simple YAML configuration file. And also we can generate observation directly to the GPU. And this is just comes from leveraging essentially the power of Habitat Sim as a rendering engine. And finally, some experiments. So we tested our implementation of A2C and DQN against a baseline, which is sort of, let's say, state of the art when looking at PyTorch, the PyTorch environment. And we compare against stable baseline on multiple classic reinforcement learning control problems. which are, Calpo here on the left side, Lunar Lander on the central part, and Acrobot, I think, on the right one. And the experiments all show that essentially we have a very similar convergence rate and performance in a very comparable amount of time as well. So obviously AvalancheRL brings about more, let's say, overhead in terms of computations, because we have many more callbacks with respect to stable baseline 3, but this is obviously to be expected. We then tested our implementation onto a continual reinforcement learning use case. So we've re-implemented the famous elastic weight consolidation, let's say, experiment in AvalancheRL with a very, let's say, simplified setting. So the idea here is very simple. We have 2 games, and we have to learn these 2 games in a sequential way without obviously forgetting any of the 2. We used a very, let's say, standard convolutional neural network, which is the same one they used in the paper and that we've re-implemented and, let's say, added to the ones you can use in AvalancheRL. And the results here are the following. So essentially, looking at the plot on the bottom part, we see that the baseline model, which is the one trained without EWC in green, ends up forgetting Breakout, which is the very famous game, obviously very popular, everyone knows it. And the model, instead trained with EWC, is able to retain most of its performance, most of its score, even after obviously having learned both games. So assuming that the performance on freeway is the same for both the baseline and the EWC one. And on the upper part, we instead see the just the effect of the EWC loss. So we see that as it happens in the EWC experiment, we first train without, let's say, any penalty, and then we add loss. Loss penalty computed by from the Fisher matrix, and then we see that the loss is is impacted immediately. And finally, we integrate both components and we test them out together. And the novelty here is that we are using a ResNet as a backbone and mapping this backbone to the 3 actions that the agent can take, so turn left, move forward, or turn right. And the motivations behind this, let's say, choice is because since we're moving toward a more realistic environment, networks such as the ResNet, which is widely used in let's say real-world settings, should perform better, and it does. And the setting is very straightforward. We have let's say an object. In this case, it's a sphere. It just plays randomly at the beginning of the episode, and the agent has to reach this object within the time frame limit of, let's say, I think it was 100 steps. And the episode will terminate upon the agent reaching the object, or otherwise when the time frame elapses. And some results here. Essentially, what we see plotted in orange is the mean reward, and on the let's say opposite direction, we see the episode length. And after initial exploratory phase, the agent learns to consistently reach the target, as we see that the episode length approaches 0. And here we should just mention that a lot of variance is to be expected in these kind of experiments, as the ball is placed randomly at the beginning of the episode, so the number of steps needed to reach the target may vary wildly. And finally, some future work on AvalancheRL. We're looking to include additional reinforcement learning algorithms, and just to say, one PPO is surely at the top of our list at the moment, and we'll also like to expand the integration with other complex environments. So as we've seen with Habitat Sim, moving to a realistic setting, we also like to have one very specific for continual learning in a robotic environment or some, I don't know, complex games. We like to keep on supporting them. We also like to implement and improve the integration with vanilla Avalanche, so as that we can make use of all the plugins that are already there. And as final notes, this work was has received some interest from the teams working on the DAPA challenge, which is this year on lifelong learning. So this is very good for the attention that this field is going to get. And obviously our code is openly available on GitHub. And yeah, that's about it. And this concludes my presentation. So thank you all for your attention and time.
Thanks to you, Nicola. Thank you really for the brilliant presentation. And it really seems a huge amount of work. So kudos to you for doing all this stuff in your master thesis. I have to say that I'm always pleased to see works on tools, reproducibility, and this kind of contribution on top of the usual new methods, new strategy stuff, which is important, of course, but it's not the only thing that matters in research, at least.
Yeah, exactly.
Yeah, and also our thesis is a very good place to perform such experimental effort. And in this case, the library, a library connecting continual learning and reinforcement learning, I think is even more than for supervised learning, is very useful because having a common setup and an experimental baselines to run in a simple way may really enable and invite new people to experiment. At least for me, in my case, I have always been, not so happy to do continual learning and reinforcement learning unless I was planning to do it for real for like 6, 8, 10 months, because it's very hard to go in this field and do a quick experimental evaluation. You have to set up lots of stuff, as you may have seen during your thesis. So
yeah, it's very tedious without a framework which does all the heavy lifting for you.
Exactly. So, well, yes, I hope that this can be well received by the community and can live on in the Avalanche, let's say, environment and ecosystem. Because yes, I'm very happy about this contribution. So I think we have a room for some questions now. Maybe I can, just to break the ice and warm things up, I can ask you one. I think that this may be a common question that came to mind if someone already knows Avalanche. So can you please expand on the contamination, let's say, between Avalanche-RL and Avalanche? So how much Avalanche-RL influences Avalanche? It is a strong dependency, so you just use Avalanche functionalities, or you modify Avalanche functionalities in order to work in reinforcement learning environments?
Okay, yeah, that's a great question. So at the moment we're trying to just use Avalanche as a let's say dependency, but the core difference here is that let's say, especially in the benchmark model, we have to support experiences which give access to an environment, to a gym environment, just to be very technical here. So an environment which exposes this kind of very well-known interface. And the benchmark model at the moment in Avalanche does not, let's say, it's very rooted into the idea of having a data set, of having a, let's say, some samples and some target and labels, let's say, and data loader and all these, let's say, concepts which come from the word of supervised and supervised learning, which it not translate very well to AvalancheRL. So in our approach was to minimize the amount of, let's say, things to change in Avalanche, so that I could then, let's say, try to merge the two forks together. So the only thing I actually changed in here was the path for the environment. So I added the support for an experience stream to give access to environments. Then all the other things, let's say I built upon Avalanche, or I did just very minor tweaks, which I can then say simply do in a different way.
Yeah, this seems about right to me also. It's kind of a, I talked before about ecosystem because it seems kind of the relationship that there is between PyTorch and Torch Vision or Torch Audio, all the ecosystem of PyTorch. I mean, those libraries heavily relies on PyTorch but do not modify really PyTorch core system. So it seems that the relationship here is similar to this approach.
Yeah, exactly.
Yeah, it's I think it's a good thing also for continuous maintenance of the projects. So I can make another question, but if there is someone from the audience, either here or in the live stream on YouTube, if someone has any questions, even mean ones, like the researchers' questions, you can feel free to unmute yourself or to write in the chat.
So I have one question, if I can, Andrea. So so thanks, Nicola, for the talk. I think this was very clear, and I'd like also to openly thank you about the immense work you have done during this master dissertation. I think you really put there the seed, for the development of this collaborative AI tool that I think many people will use and be interested about. That said, I also acknowledge the fact that it was difficult to find some commonalities between the utils that we have developed for the supervised learning, let's say, world and Avalanche and the reinforcement learning one, since as you explained, the assumptions about the where the data come from, where the actual agents makes its actions, and a lot of different things result in a difficulty in reusing a lot of assets we have developed within Avalanche. But not in a sense that Avalanche is not general enough, but more in a sense that what we do in supervised learning and reinforcement learning is fundamentally different, so that it's difficult to find ways to have a more general and utils that can be used to build things on top in a shared way. So that was the intent of your own effort and this idea of AvalancheRL, of course. But we found these issues. So in my own vision, the best way to share things across libraries was the plugins, let's say, dimension. Because you have done a very good job in having the same callback systems for the two, let's say, base strategy and the RL base strategy, so that you can actually reuse plugins, and that would be, I guess, in the future the best way to create new strategies and to develop strategies just through plugins. So I wanted to ask you if you see this to be possible in the future, so that if you envision the possibility of having, let's say, shared plugins, with the core, let's say, technical strategy-focused improvements, like algorithmic improvements to make continual learning work, despite the specific loss or maybe the settings in which we operate. So if that would be possible in the future, or if you think that AvalancheRL would be mostly instead creating its own instantiation of plugins, or just have use inheritance or other techniques to specify, let's say, these plugins better. So this is more or less the question. So how you see plugins being developed in the future across Avalanche, AvalancheRL, and if it wouldn't impose much complexity on the overall Avalanche ecosystem, this idea of having general plugins.
Yeah, that's thanks a lot for all the compliments, and this is our question because let's say we in general for just as much to generalize from, which is the core, let's say, problem between data sets, fixed data sets, and generated data set. It's not always easy, and probably the easiest solution would be to let's say have some sort of theme level of generality, in which we support some plugins support both, and some just work for supervisor and supervised. Just to be more specific, probably we can make that work if we had something like a data loader, which is used all around Avalanche code base. If we had like a data loader which abstracted away the fact that data is, instead of being, let's say, given from a fixed data set, if it was abstracted away the fact that the agent interacted, the, let's say, backstage, and then give this, let's say, data at the same time, you could iterate these data set, then yeah, probably you could do that. But you'd have to specify some other parameters, which is how many interactions you want, because data set can be infinite in RL. So yeah, I see that. Just to be short, first thing I would do is try to be, let's say, not to encompass all possible solutions, but just a short amount of them that you can, let's say, have some plugins which are shared and some that instead only rely on supervised and unsupervised.
Thanks. I agree with you. It's for example, for replay, I always imagine that would be fairly, general. But again, when you want to generalize things in terms of practical changes and a level of abstractions and of complexity that in the end you introduce, that's always, I think, a concern, because we have seen over and over again that complexity is a real enemy for easiness of use, and that's fundamental for us with Avalanche. So we would rather duplicate a bit of code or work on incremental solutions rather than add too many layers of abstractions just to make this work on a theoretical level, right? So it's always a trade-off. Yeah. We will find the right way, I think.
This will try.
Yeah. Let's remember that this is really the first effort in trying to bridge these two very different approaches, like supervised, unsupervised, and reinforcement learning. So even if, let's say, let's call it a proof of concept, but I think that it shows that it is actually possible to merge these two libraries. Of course, you have to give it something. So, for example, maybe the plugins. Yes, replay plugins are reusable, maybe because replay is something bundled also in RL, not only in supervised. Maybe some others will not be immediately reusable, but I think that even having a small, coherent, and effective libraries for continual reinforcement learning may really help in starting, because as I was saying before, it's very scary to start from scratch, also in RL, but in continual reinforcement learning, there is all another level on top of it, which may scare some people, including me, out of and away of this interesting topic. Okay, so thank you also, Vincenzo, for the initial talk and then the final question. And so if there are any questions, from the audience? Any other curiosity or issues you may find? Okay, but I mean, you can take your time and check the project on GitHub. It is hosted currently also on the ContinualAI account, so I mean, it's good also to have such an organization that gathers together the open source contributions. And in case you liked it, you can also contribute to either Avalanche, AvalancheRL, ContinualAI in general. Get involved, get in touch. We are very pleased to if you do so. And
yeah, sure. I didn't mention it, but if you feel like you can, just play around with AvalancheRL, or you have some idea or just want to contribute, feel free to reach out to me, or just open an issue on GitHub, and we'll be right on it.
Yeah, great. So I would say that we can thank again Nicolò for the amazing presentation, and I'll see you all in the next Continual Learning seminar session, happening as always on Thursday, 17:30 p.m. chat. So stay healthy, stay safe. Goodbye everybody, and see you soon.
Thanks again.
Bye. Thank you so much, Nicolò and Andrea. Bye. Thank you all.
Bye.